Welcome to this webinar in which I will show you how to build a multi-node microgrid EV infrastructure project for the UC San Diego campus. And on your screen, you see the high-level schematics of the system. It's a very distributed system. You can see here with the orange lines, the cables. Here, for example, we have transformers, and we already have existing distributed energy resources on our map here. The goal now is really to design the system at minimum costs to host additionally 40 DC fast chargers, and at the same time allow additional distributed energy resources at minimum costs at strategic places within the system so that we're not burdening the cables and transformers too much. And with this strategic analysis, we can actually add this 40 additional DC fast chargers and only have to upgrade a couple of cables and one transformer. And now I will talk you through this process. So from our perspective, it's really important to consider the underlying topology network of the infrastructure because there are losses in the system. It's a distributed system, as you have seen, the cables, transformers, and there are losses for the energy that flows between these different nodes. And those losses need to be considered because the losses have to be supplied either through utility, which can increase the cost, or through distributed energy resources, which you want to install. When considering this, you can take from a catalog certain cables and transformers, or Xendee can auto-design the system for you so that you don't have to deal with this, and it tells you where to actually upgrade the cables and transformers for you. The next important part for such an EV infrastructure project is probably to define also the building loads, because most of these projects are also connected to real buildings. They are in a community, so they are not in isolation, these EV chargers, from a wider microgrid. And there's a good chance that you have to model electricity, heating, or cooling loads, and you can upload those loads, or you take it from our database. The next very important stuff for an electric vehicle project, of course, is to define the electric vehicle demand. There are multiple ways of doing this, and the simplest way that you will see here now is to just upload historic load profile patterns or some anticipated ones. But the reality is you probably don't have a good idea for this, and this is why we have a different way of doing this. We have an EV consumption builder, which allows us to actually estimate for a database of electric vehicles, trucks, on how much we can expect to charge those cars at the end of the day when they come back into a depot. And then we can now create an availability curve, which you will see soon on your screen, which tells us when the cars are back and can be charged. And with this now, Xendee actually can decide when to charge those electric vehicles at minimum costs, or even defer charging to reduce costs here. So Xendee can actually decide if we use the utility, if it's cheap enough, or if we have surplus electricity, we could use it from the distributed energy resources, or maybe we completely shift it. So in the next step, we need, of course, electricity rates. They are a very important driver for microgrids and EV infrastructure projects. I mean, demand charges really can contribute a lot in terms of costs. So we want to probably optimize such a project against utility costs. And here we can bring in through APIs real-time information about the electricity rates, so up-to-date information. In this case, it's San Diego Gas and Electric, and then use this for your building electricity loads or for your electric vehicle charging infrastructure. Of course, you can modify those tariffs directly in your system. We have a high flexibility here, so we can define a lot of different periods of time. We can modify demand charges. We can add tiered rates, and we can also add market rates or real-time pricing if you want to do this. So far, we have defined the system from a topology perspective. So you see basically that we are defining here these orange lines, the cables, transformers. We started adding the electricity loads, and we also assigned the electricity rates for those different buildings. So the next step is really to identify the technologies that we're interested in. And the first, of course, is to define our charging infrastructure. So Xendee has different ways of doing this. The simplest ways you can force, like you see on the screen now, that we already have existing numbers, or we force certain numbers of charges in the system. But of course, Xendee can also decide on how many charges we might need for this. So let's say we have a certain demand. Now we can ask the question, what type of charges should we install, and how big those charges should be. There's also the possibility to consider, of course, different levels. Could be level 2, level 3. And also there can be incentives for certain programs that we can consider here. And also if we have enough space for these different charging stations. The next thing is to define our distributed energy resource technologies. So batteries, generators, PV systems, maybe other technologies in the system that we're interested in, and we think will help us to bring the costs down for our project. Here you see on your screen how we deal with batteries. We can take them from a catalog. The catalog system is fairly large. You can, of course, define, override different parameters, and you can actually specify where you think these batteries should go in the distributed system. And then at the end, when we do the optimization with Xendee, it will actually decide if a certain battery at a certain node makes actually sense. There are, of course, other technologies. In this project, we defined photovoltaics, fuel cells, other technologies which follow the same principles like you have seen for the batteries. But now I want to talk a little bit about project financing, because the financing will really impact the solution space here. What technologies are attractive? There are different financial methodologies that you can model. A very simple way is to use amortized capital costs, which basically amortizes the investment costs of a certain technology over its lifetime. The other ways, like a loan purchase, you could do an energy as a service, and you will see that all these different ways on how you finance your project will impact your cost savings and technologies that you will see in the solution here. So when you have defined the loads, the electricity rates, the technologies that you're interested in, you can define the objective for your optimization here. And there cost minimization, there could be a CO2 minimization, there could be actually increased resiliency that I'm interested in. Key here is that I'm not telling the system when to charge a battery, for example, or when to run a generator. We are telling the system all the information about those technologies, as we did, as you have seen, around cost, availability, and so on. And then in combination with the objective, Xendee will tell us what technologies will be attractive and how we should operate them. So this is the first result for this UC San Diego case. This is really for amortized capital costs that are used, cost minimization. And whenever we do such an analysis, we compare it to a reference case. The reference case being the existing situation. So in this case, with UC San Diego, the existing level 2 chargers and some of the DC chargers with the existing DRs at this side, because UC San Diego is actually a microgrid, already has some gas turbines, steam turbines, PV, batteries, and fuel cells. So we modeled them as existing as a reference case. And then we were now interested in how we should upgrade the system with additional chargers and renewable energy technologies to reduce our carbon emissions costs, and at the same time, for example, to avoid lengthy interconnection times with the utility. So against the reference case, now we can save almost 12% in terms of costs and 15% in carbon emissions. But the key here is that Xendee tells us how big the total PV system should be, how many chargers we need, and where to place all these technologies. Because remember, at the beginning I said, we can model the energy flow and the power flow in the system. So now Xendee has an understanding of how the energy is flowing, where there are bottlenecks in the cables and transformers. And with this strategic placing, actually, we can avoid expensive upgrades to the underlying distribution system. As I mentioned, only a couple of cables and one transformer need to be upgraded with this approach. So In terms of results, Xendee does not only give you the investment capacities and saving, it also tells you on how you can expect to run those technologies. And you can have this for every day, within a year, for every node. And in this way, you see how energy is flowing between the different nodes and how you utilize the technologies on different days. Here by node, you can actually see how the energy flows between nodes. So for example, what is imported from one node or what gets exported to another node. And this in the background, of course, is helpful because this allows us to calculate the losses in the system or avoid this costly cable and transformer upgrades. And here we have the result from this optimized power flow in the distribution system in the local one. And you can see that it actually calculates here all our losses for the energy which flows between these nodes, the minimum, the maximum power that flows here. And also it tells us where we might have voltage problems in the system because of renewables or too much charging. In this case, everything is okay. And we have some under voltage, but it's very minor. So now let's go back to the financing. As I said already early on, the financing will change the results. And the first results that I have shown you was around amortized capital costs, which basically amortizes the costs of the investment over the lifetime of each single technology. In amortized capital costs approach, which comes from the utility space, there's no project lifetime. And in this way, you can very easily compare technologies with different lifetimes. For example, you can easily compare the attractiveness of a long-lasting technology like PV with maybe a battery which only lasts 10 years, right? If you go to a loan purchase approach, which has a project length in it, you might actually change without knowing the results against technologies which have a shorter lifetime. So let's assume we have a lifetime of a technology with 30 years and the project lifetime would only be 10 years. Then a PV system which lasts for 30 years only gets considered for 10 years and the rest gets actually neglected the last 20 years. So in this way, actually, technology which only lasts 10 years has an advantage compared to a technology with a longer lifetime. And this is why we use amortized capital cost approach sometimes. But of course, if you don't care what's happening with the project after project life length or lifetime, then of course you could go with a net present value approach, loan purchase approach. So now I changed this to loan purchases. We say that we want to finance 85% of the project through the loan. There's the loan length. The project length was set now to 30 years. And now, just to give you an idea here, you will see that the results change. The PV system stays constant, but actually now with the loan purchase, because of this changed assumptions, we actually see less charging infrastructure than we would have seen with the amortized capital approach. So bottom line is, we should really carefully think about the financial methodology when we do such analyses. So the last thing I want to bring up is actually multi-year analysis. So when we do a microgrid project or EV infrastructure project, you probably want to simulate the impact of changes over time. Electricity rates can go up, and they certainly go up. Performance changes, right? For example, the battery and the PV system degrades over time, or generators. So you want to model all these factors over time so that you can assess actually your revenue stream, for example, if you're providing a software as a service contract to a client. And here you see the result of such a multi-year analysis. You can see that we're starting here in the red because we have to install new equipment. Over time, of course, we are saving against the reference case. Then we get into the green, but here in year 11, we have to reinstall the technology because of lifetime, which brings us slightly negative again, but then we're going up into the positive. So it actually shows you nicely on how you can expect the revenue changes for you. So to summarize all this from our perspective, if we want to do a very careful analysis of an EV infrastructure project, we should consider 4 important points. First of all, to consider underlying topology network, to consider losses. The other thing is to use an optimization approach like in Xendee that not only tells you the investment capacity, but also how you can plan to run those technologies. You have seen this with this dispatch curves between the nodes and for every day. As already mentioned out, modeling the impact of different financing schemes might be very important. And of course, then showing the impact and analyzing the impact of changes over time is really key, because you're not building this project just for 1 year, you're building this problem for 10, 15, 20 years, and you want to hedge against some expected or unexpected changes over time here. So this brings me to the end of my webinar. I hope it was really helpful for you. So thanks for joining here, and see you the next time.